Today's space missions rely mainly on the usage of chemical propellants. Deep space probes have relied on chemical propellants for thrust and radioisotope thermoelectric generators for heat and power generation. While this has been successful for probes and moon landings, further exploration of space, including a manned Mars mission, will need propellants that can reduce the flight time for astronauts and provide high specific impulse values for the vehicle. Nuclear fuel has an energy density orders of magnitude greater than chemical fuel, which can improve specific impulse values, reduce travel time to and from distant objects and planets in space, and provide an electric, heat, and power source. The formation and evolution of Mars are comparable to those of Earth. This means valuable information about Earth's history and its future can be gained by studying the once habitable Mars. Nuclear propulsion technology makes the journey to Mars that much more realistic by reducing the needed travel time, providing power with thermoelectric conversion technology, and a heat source in the form of decay heat.
It is clear that space travel will require new technologies beyond conventional propulsion systems. But that leaves the question of why space travel is important at all. Space is a dangerous place, and the Earth has everything we need to survive, right? Unfortunately, this isn't the case, as the Earth has a finite supply of resources. According to a report released by BP at the end of 2013, the current world oil reserves have reached 1.7 trillion barrels, which at the current consumption rate will last us about 52.5 years. According to the World Coal Association, there are an estimated 892 billion tons of coal, or just about enough to last for 110 years at the current consumption rate. Even nuclear fuel has a finite supply, with known resources of uranium being 5.9 million tons, or just enough to last 90 years, according to World Nuclear. A few important things to note about the uranium supply numbers is that these do not include civil stockpiles, re-enrichment, or reprocessing. Renewables are an important fuel source that deserve mentioning here, especially since they are not subject to the same limited reserves as the aforementioned fuels. However, for reasons that are beyond the scope of this video, they are not likely to be suitable as the sole energy source for our planet. The energy density of a substance refers to the amount of energy of a substance per unit mass, which is usually expressed in the amount of extractable energy, and is typically called specific energy. As you can see here, the energy density of uranium is orders of magnitude larger than coal, or even typical solid rocket fuels, which make it an ideal candidate for space travel. What this all really comes down to is, can chemical fuels remain as the primary energy source for propulsion in space? And how will we meet the growing energy consumption needs going into the future?
We have all seen a rocket fly, either live or on television, but what is the science behind it? It all comes down to Newton's third law of motion, which states that every action is an equal and opposite reaction. The rocket uses the propellant, which is a rocket fuel that combusts backwards with great force in order to push the rocket forward. Specific impulse helps us determine how efficient a rocket is. It's dimensionally equivalent to thrust over propellant flow rate. And finally, the ideal rocket equation helps us determine the velocity of the rocket. What is thermal expansion? Well, thermal expansion of fuel is a change in shape, area, or volume of fuel due to change in temperature. Combustion of solid or liquid propellants creates gases at high pressure. The nozzle uses the heat energy released by the expansion of the gas to accelerate the rocket at very high supersonic speed. The thrust-to-weight ratio is a quantity used to identify how much propellant should come out of the rocket at any moment. The ratio can be simplified to force over weight, or acceleration of the rocket divided by gravitational acceleration. As long as the ratio is about 1, the rocket can accelerate vertically upwards.
A fusion rocket is a theoretical design for a rocket driven by fusion power, which could provide efficient and long-term acceleration in space without the need to carry a large fuel supply. There are two major types of propulsion that fusion rockets can use. One is electric propulsion, in which a fusion reactor powers an ion thruster. The main alternative would be to have a direct conversion into kinetic energy using advanced confinement techniques. The main challenge against fusion rockets and even a self-sustaining fusion reactor is confinement. The two types of confinement are magnetic and inertial confinement, each with benefits and drawbacks.
When comparing fusion rockets to chemical rockets, some key factors to take note of are the thrust and specific impulse of each type. Specific impulse is a very good indicator of engine efficiency. Impulse is thrust created over a given amount of time, and specific impulse is the impulse divided by the rocket's mass. The specific impulse value for fusion rockets is much higher than that of both solid and liquid fuel chemical rockets, indicating that the fusion rocket can produce much more thrust for the same amount of propellant. A drawback of fusion rockets, however, is seen in the rocket's thrust-to-weight ratio. In order for a rocket to achieve takeoff, the thrust-to-weight ratio must be greater than 1, and the numbers here show a thrust-to-weight ratio of only 0.035 for a fusion rocket, while the solid fuel chemical rockets has a ratio of 2, and liquid fuel chemical rockets have a ratio of 58.
To conclude, rockets that harness the power of nuclear fusion will be the next big leap in humanity's quest to explore the final frontier. Nuclear fusion rockets could slash travel times through deep space, potentially opening up vast swaths of the solar system to human exploration. Nuclear propulsion is the best near-term method for powering rockets for deep space exploration. The engine offers lower cost and quicker travel times. By contrast, chemical propulsion is bulky, heavy, expensive, and slow. Despite using it for several decades, continued use could potentially raise costs to unaffordable levels. The ability to explore deep space is in the best interest of the survivability of the human race. Many well-known scientists and physicists believe that staying on Earth will lead to the extinction of the human race. Some of the reasons given for this are the lack of natural resources, comets, nuclear war, and worldwide epidemics. Stephen Hawking, renowned British theoretical physicist, said, "I don't think the human race will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet. But I'm an optimist. We will reach out to the stars."